Hi and welcome to this TY Higher Level Maths Indices Revision Module video. So this video series we put together to help you move from the Junior Cert Higher Level course to the Leaving Cert Higher Level course. So this video today is going to look at surds. So surds themselves are connected to indices, so it is important that if you haven't already done so, that you revise your rules of indices using the indices video in this series. So surds we see quite a bit. They come up in the form of asking you to give your answer in surd form. Today we're going to focus on using the rules of surds, or they're more correctly known as the property of surds. So let's work through this. So now we're going to move on to surds. So before I talk about surd equations, I just want to go over surds in general. If you just want to look straight away at the surd equations, feel free to skip over. Make sure that you are happy with surds. I suppose surd equations can be asked and other types of questions on surds can be asked. And I suppose some of them mightn't feel relevant here, but I just would like to cover all of the surds together. So surds is just another name for a number which can be written as square roots. Basically what I'm talking about is root 2, root 3 and root 5. So root 4 wouldn't technically be a surd because root 4 simplifies to 2. So any number which is written with a square root, we often call that square root the surd. So we call these surd numbers. So you remember that these numbers are irrational, so hopefully you remember that. So they're infinite non-recurring decimals, so this means they go on forever after the decimal point and they don't repeat themselves. So any decimal version you write down will have rounding. So using this surd form is the most accurate way of writing the number. So for example, if you have your calculator in front of you and you want to do root 2, most new calculators now, if you type in root 2 equals, you'll get back root 2 and you'll have to use the change button or the SD button depending on which calculator you're using to figure out what it is as a decimal. So the square root of 2 gives me, and I'll actually just write it in here so you have it. So square root of 2 equals 1.4142135562, and that's where my calculator stops because that's where I've set it to stop. Some people's calculator might do less, some people might do more, but that has been rounded. You might look at it and say, well, really? But actually it has. So if you take that number and you square it again, so type into your calculator 1.4142135562 and square it, you actually get 1.99999. So actually we've made it inaccurate, we've rounded it. So using the surd form is much more accurate than putting it into decimal. I know people don't like the surd form, it's similar to the fractions, but it is the most accurate way. So looking at the properties of surds now, so there are really three that you need to know and you need to be able to work with. And that is, if you have the square root of AB, which means A multiplied by B, you can separate that out. It's like the square root of A multiplied by the square root of B. So if you think of it like this, I have A multiplied by B. That's the same as the square root of A multiplied by the square root of B. So I suppose you could look at this as the multiply can happen underneath the square root or outside the square root. So the second property you need to work with is quite similar. It's about a fraction. So if I have a fraction, and remember with fraction we have division. So really what this is, if I have A divided by B under the square root, it's the same thing as A, the square root of A divided by the square root of B. So remember that fraction means division. So those two are like the opposites of each other. Okay? And then the last property that we have is the square root of A by the square root of A is the square root of A squared, and that equals A. Okay, so basically the square root of A is equal to the square root of A is equal to the square root of A squared, and basically what happens is the A squared and the root, they cancel, so I'm just left with A. Okay, so we can work both ways with that. It's like the square root squared, or you can use it like we had in the first property, that actually you're working backwards, you're putting them back under the same square root. Both will lead us back to A. So it's also important that you're familiar with the perfect squares. So we would have talked about this when we did our factorization, specifically the difference of two squares. It's also quite important to know when you're talking about squares, we will talk about completing the square in different areas, but what we're talking about then with squares are these numbers here. So 1 is a perfect square, 4, 9, 16. So perfect square is a number whose square root is a whole number. So for example, 16 is a perfect square since the square root of 16 is 4. So I would definitely make sure that you know all the way up to 169. So we have 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and 13 squared. And I do know that you may not have come across 13, but they do love to throw this in, especially with the difference of two squares. 169 is 13 squared. Okay, you can always check on your calculator if it is a perfect square, if it's a much bigger number, or if it's one of those numbers and you just don't recognize it. You can use your square root button. Okay, so for example, if I gave you the number 196 and I said, is that a perfect square? Well, what you would do is put into your calculator square root of 196. So if you have your calculator in front of you, try it now, and you should get 14. So you'd say, yes, it is a perfect square. If I gave you the square root of 2, or sorry, if I gave you the number 200 and asked, is that a perfect square? Same method, we do the square root. So if you can do that now, put it into your calculator, and what you'll find is you will be left with a surd in the first instance if you're using a new calculator, and what the new calculator will give you is 10 root 2, and if you convert it, it gives you 14.14 on. And basically what that means is it is not a perfect square. So that one is not a perfect square, that one is a perfect square. So just get used to using your square root buttons to help you out in case you don't recognize a number. So let's look at using these properties of surds. Okay, so simplify each of the following. So the method that we use to simplify surds is we're going to try and see, is there a perfect square that will divide into the number? So think of your perfect squares. Okay, we have 1, 4, 9, 16, 25, and so on. Looking at that first one, hopefully everyone will see that 99 can be written as 9 times 11. Okay, and using the first property of surds, we can write that as the square root of 9, square root of 11, and we can simplify the square root of 9 to 3 root 11, and that's your answer. So always the same method. Is there a perfect square that we can divide in? So let's work for the moment just with this bit here. Let's not forget it. I'm going to highlight it because often we can forget it. So I don't want to forget it, and actually it might be easier for us to keep it as we work through our surds so we don't forget it. So square root of 112. So what is the biggest perfect square that can go into it? So we could say 4 goes into it. Does anything else go into it? Well, 16 goes into it, and you can check that. So basically, I can separate this into 16 times 7. So what you could do is you'd say, well, the first perfect square is 1. That's not going to be of any help. The next one is 4. So 112 divided by 4. But that gives me 28. And when you see the number 28, hopefully you know that 4 also divides into that. So you'd say, well, actually 4 isn't the biggest perfect square that goes into it. So we're going to get a half of the square root of 16 by the square root of 7, which gives me a half of 4 root 7, and a half of 4 is going to give me 2 root 7, and that's my answer. Okay, so now we have 2 1/4 under our square root. So in maths, we very rarely use these type of mixed fraction where there's a whole number and a fraction. More likely we are going to use either an improper fraction, okay, or a decimal, okay? So depending on the question. We're going to use an improper fraction or a top-heavy fraction. So hopefully you remember how to do these. The method is 4 by 2 is 8 plus 1, so it gives me 9 over 4. So this is a real flashback to primary school. Hopefully you remember that. Okay, so if you remember our second property of surds, we could rewrite this as root 9 all over root 4, which gives me the square root of 9 is 3 and the square root of 4 is 2. Okay, so these aren't overly complicated, but they do require some practice, like everything, because it's very easy to look and say, oh yeah, that's simple. But sitting in an exam, if you haven't seen them in a while, you might panic and say, I can't remember how to do this. So we're always just trying to find the biggest perfect square that we can divide in. So let's look at example 6. So here we're going to just put a few different simplifications, or a few different of the simplifying together, and then we're going to add and subtract. So express the following as a surd in its simplest form. So this should be one surd, so there's very little I can do with it at the moment. So what I want to find is, I want to find what perfect square will divide into 180. Okay, so I could divide 180 by 9 and I get 20. And 20 is divisible by 4, so it's not the biggest. So you can go up, and hopefully what you'll find, through a little bit of trial and error if you need to, is that this is 36 by 5. Okay, 20, hopefully you can see very quickly, is 4 by 5 minus, and this is 25 by 5. So what I'd like to point out at this point is we have a perfect square of 36 and a 5, the perfect square of 4 and a 5, and the perfect square of 25 and a 5. So if you were able to find, or able to simplify one of them, and I suppose the one that I would lean towards is the root 20 because it's the simplest, it's the square root of 4 by 5. So the 4 is the perfect square. So if we were to simplify this, it'd be the square root of 4 square root of 5, which will give you 2 root 5. Well, in order to add and subtract, all of those terms would need to have a root 5. So once you have this root 5, you could then really simply divide 5 into 180 and you'd get your 36, and 5 into 125 to get your 25. Okay, so you can do it either way. If you're happy to work with trial and error, or you can be clever about it, work out the simplest and say, well, if I'm going to have to add them, because they did ask for a surd, so they will add and subtract together, they're all going to have to have that square root of 5. So let's tidy up here. So what we have now is square root of 36 by square root of 5, and the square root of 36 is 6 root 5 plus, we still have our 2 root 5, and let's clean up the last term here. It's going to be the square root of 25 by the square root of 5, which is minus 5 root 5. So what I have here is 6 square roots of 5 plus 2 square roots of 5 minus 5 root 5. So I suppose if you think about this as a thing, so I have 6 of something, I add 2 of that something, and then I take 5 away. Okay, so even if we want to say apples, so I have 6 apples, I add 2 apples, so I have 8 apples, and I minus 5 apples, so I have 3 apples. Okay, and I think everyone will be well able to do that. But the square roots are worked in the exact same way. I have 6 of the square roots of 5. Then I add 2, so now I have 8 square roots of 5. And now I'm subtracting 5. So what I'm left with is 3 root 5. So they're added like they are things. Okay, so I have 6 of this thing, I'm adding 2 more, and then I take 5 away. So I'm left with 3 of those things. And I know it's kind of a hard concept to get your head around, but like I said, practice with the surds is really the only thing that will improve with this. It will help you improve your work. So now let's take a look at an example of multiplying out surds. So in this case we have one bracket. So it works very similarly to algebra, we multiply root 5 by the first piece and root 5 by the second piece. And don't forget your sign. So root 5 by 1 is root 5 minus root 5 times root 5. So here, root 5 by root 5 is root 5 squared, which gives us 5. And our final answer here is root 5 minus 5. If you were given a question like this, you can use your calculator to maybe help you between the steps. So if you wanted to kind of work with this to help you get to 5, but do not enter it directly, because what we need to be able to do is to work with examples like this even when they're not numbers. So it is important that you're able to show your work and you don't just use your calculator to get a final answer. You can of course use your calculator to check your answer, and I highly encourage this. So let's take example 4, multiplying out surds. And in this example we have 2 brackets. Just like algebra, when we're working with 2 brackets, our working method is to split that first bracket. So we get 3 times the second bracket, which is 5 plus 2 root 7. Then minus root 7 times 5 plus 2 root 7. And let's multiply that out. We get 3 by 5, 3 plus 2 root 7, minus root 7, what's your signs? And minus root 7 times 2 root 7. So 3 times 5 is 15. 3 times 2 root 7. So multiply the rational parts by each other. So the 3 by 2 gives me 6 root 7. Minus root 7 by 5 gives me minus 5 root 7. And here we get minus 2 root 7 times root 7, or root 7 squared. So cleaning this up, we can add these two together. So 6 root 7 minus 5 root 7 is plus root 7. And root 7 by root 7, we said was root 7 squared, which is 7. So 2 times 7, 15 plus root 7 minus 14, which gives us 1 plus root 7. So sometimes students really struggle with working with surds in this way. So one suggestion I have is to treat this surd like you would treat an x. Okay, so if you can imagine everything I've highlighted there as an x, it might make life a bit easier. So 3 multiplied by 2x would be 6x. So 3 times 2 root 7 is 6 root 7. Similarly, when we're adding 6 root 7 minus 5 root 7, think of what you'd do if there was an x. What is 6x minus 5x? So that would leave us with just 1x or x. So similarly, 6 root 7 minus 5 root 7 would give me root 7. Root 7 multiplied by root 7 would give me root 7 squared, the same way that x times x would give us x squared. So sometimes it is a good idea to think of the surds like we would think of a variable in algebra. So let's take an example of where we want to rationalize the denominator. So as we discussed, these surds are irrational numbers, which means that they cannot be written in the form of a fraction, and if they were written as a decimal, the decimal will be non-repeating and it will be non-terminating. So it does not end and it does not repeat. So if I want to rationalize the denominator, what I'm trying to do is to remove the surd from the denominator or the bottom line. There's a few different ways we can work with this. What I'm going to do first, I'm going to work through it with multiplying the top and the bottom by root 8. So what I'm doing here is I'm multiplying it by a fraction, which is effectively 1. But when I multiply that denominator, root 8 by root 8, I'm going to end up with 8. Okay? Because root 8 by root 8 is root 8 squared, which is 8, and straight away I've rationalized my denominator. I then have root 128 minus root 50 times root 8. It might be a little bit easier to work with the root 8 going first. So root 8 times root 128 minus root 50 all over 8, and let's multiply it out. So I get root 8 times root 128 minus root 8 times root 50 all over 8. Now, our numbers are quite big here, so you can use your calculator to help you. So I have 8 times 128, so I get 1024. So I get the square root of 1024, and I do 8 times 50 minus the square root of 400 all over 8. Using the rules I've already learned to simplify our surds, we can work through this, but what you'll find is 1024 is actually a perfect square, so the square root of that is 32. Similarly, the square root of 400, because 400 is a perfect square, is also will give us a nice whole number. So we get 32 minus 20 over 8, which gives us 12 over 8, which gives us 3 over 2. Now, a second method we could use to do this is to actually do a bit of simplifying first. So simplifying down our square roots, like we've already seen, root 128 simplifies to 8 root 2. The square root of 50 gives us 5 root 2. And root 8, if I simplify that down, gives us 2 root 2. So now you can see that there is actually some things in common. So we can clean up. 8 root 2 minus 5 root 2 gives me 3 root 2 all over 2 root 2. The root 2 is common, which simplifies or cancels down, or we can think of it as dividing root 2 into the top and the bottom, leaving us with 3 over 2. So in this case, you can see that actually simplifying each of those pieces first made our lives a lot easier and the sum a lot simpler. It won't always be the case that we can do this, so it's important to understand how we can rationalize the denominator if it does not simply cancel, or the third part does not simply cancel away. So now we're going to look at our final example, which is rationalizing the denominator using what's called the conjugate. Now the conjugate of a third expression is similar to something we're going to see as you move into another section of the Leaving Cert higher level course, which is called complex numbers. So this word is something you will see again, so it's important you remember it. So simplify the following expression by rationalizing the denominator. Now this is incorrect, so please don't write it down. But the biggest mistake the students make is they say, well, if I have 1 minus root 3, simply squaring it will get rid of that square root. Okay, so multiplying it by itself. So think of that as 1 minus root 3. But actually, what happens when you square that? You square the first piece. Minus, so we're going to have minus 1 times root 3 and then double. So you get minus 2 root 3. And then you're going to get plus 9 here at the end. But notice we don't actually get rid of the third. There's still a third piece there. So by simply multiplying it by itself, that's not going to happen. However, if I instead took what we call the conjugate, okay, and the conjugate is when you multiply it by 1 plus root 3. So it's the same expression, but we simply change the sign of, in this case, the third. So we just change that middle sign. So if you multiply that out, we end up with 1 excuse me, minus root 3 plus root 3 minus 9. And the root 3's cancel, and I'm left with minus 8. So we're left with a lovely rational number. So it's important to note that squaring won't work. Instead, we have to use what's called the conjugate. So to get rid of that bottom line, I'm going to multiply it by 1 plus root 3. Okay. So I don't want to change this fraction. I'm not allowed. So I have to multiply the top line by 1 plus root 3 as well. When I simplify down that fraction, that simplifies to 1, which means I'm not actually changing anything. So I get 12 times 1 plus root 3. And I get, from my workings out on the other side, this actually works out as minus 8. So I get 12 plus 12 root 3 all over minus 8. So when you multiply it out, there's not a huge amount you could do. But if we go back to this step here, we could have simplified down. So we could say 8 and 12 have a common factor of 4. So that goes in minus 2 times, and this goes in 3 times. So actually by multiplying this out, it doesn't help us in any way. So we actually get 3 plus 3 root 3 over minus 2. And that is simplified down. If you worked it in a slightly different way or with the signs different, you could end up with minus 3 root 3 all over 2. That means exactly the same thing.